Hi everyone. Let's take a look at example 2 in our optimization notes. So example 2 says a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? So, the first thing with a question like this is establishing what the scenario looks like, and more importantly, what the purpose of each of your variables is. And it doesn't matter whether you use L and W, X and Y, base and height, right? That makes no difference whatsoever, right? But let's look again at what the question says. The rectangle is adjacent to the river, adjacent meaning next to, right? Excuse me. And then it also says no fencing is needed along the river, right? So this rectangle, right, actually only has three sides fenced. Okay, so that's what's going on in my picture. And now we also remember with the rectangle, opposite sides are congruent, so that's why I have two X's and just one Y. Okay, so excuse me. So what are we trying to optimize here, right? So we look back at the last sentence. What dimensions would require the least amount of fencing if no fencing is needed along the river? And this is where you have to think geometrically, right? And you have to go, okay, how can I measure the amount of fencing, right? And that would be perimeter. And so based on my variables, the perimeter would be 2x plus y, okay? So that's my primary equation, right? And now, what's my restriction? What's preventing me from making x, 0.5 and y 0.75, right? Well, we are told that the pasture must contain 180,000 square meters, right? And so square meters, the units are key here, right? Because this is an area calculation. And so my secondary equation, right, is that 180,000 must be x times y, okay? So we can take that equation, right? We can go ahead and rewrite it. Now it's your pick what variable you want to solve for, right? I went ahead and solved this area equation for y because in my primary it was just plus y, right? I don't have to do any additional algebra. If I'd solved for x, is it hard to multiply it by 2? No, but it is an extra step and I don't want to do that. And then what are some other restrictions, right? This is where you have to remember the context, right? This is supposed to be like a real life scenario, right? Could you make a rectangle if x or y were 0? No. Could you make a rectangle if x or y were negative? No, right? So similar to example 1, x and y both have to be greater than 0. Okay. So, excuse me, we'll come back to those. Let's go ahead and take our equation for y and plug it back into our primary, and that gives us our primary function. So here is our perimeter as a function of x. So p of x is 2x plus, and now I've substituted in for y, 180,000 over x. Okay, so this is the function I am going to be finding the minimum of, right? Because the question said least amount of fencing. So that's what I'm looking for, okay? So before we get to that, excuse me, let's talk domain. So I'm going to use my secondary rewritten, right? I know y equals 180,000 over x. I also know y has to be positive. So, and I also know x has to be positive. So in terms of domain, right, I know that x has to start off being greater than 0, right? And now this one's a little tricky, right? If I take those two values with y, the equation and the inequality, so 180,000 over x is greater than 0, right? A lot of people are going to look at this and say, oh yeah, the upper bound for x is 180,000, right? But why, right? What happens if x is a million, right? What's 180,000 divided by a million? Is that greater than 0? Yes, it is, right? And so the upper bound for x here is actually infinite. Okay, right? Now, some of you might be like, what? That doesn't make sense. But theoretically, could you make a rectangle, right, where x was a billion meters long and then make y infinitely small, right? Yes, you could, right? You could do 180,000 divided by 1 billion and get a y value. Now, is that a realistic, area for your herd, right? Probably not, okay? But we're not concerned with that, right? Because then we would have to know what's the size of the sheep or the cows or whatever this is a herd of, right? So we don't have that information. So we just have to explore the possibility. Could X be a million, billion, trillion big meters long, right? And the answer is yes. Is that an insane rectangle to make? Yes. But could we? Yes. Okay. So now that we've established that, let's go ahead and find our critical numbers. So first thing we need is the derivative. So p prime of x is 2, right? And then 180,000 x to the first, or excuse me, x to the negative first, if I rewrite that, just go ahead and do power rule, would give me minus 180,000 x to the negative second. And then I went ahead and rewrote it. You know, we're going to have to solve some equations, right? We're going to have to set it equal to 0. We're going to have to set it equal to does not exist. When you're going to solve an equation, I actually don't like writing negative exponents. In general, I don't like negative exponents. But in this case in particular, it's going to be easier to solve if you don't have x to the negative second in the numerator. Okay, so let's set this equal to 0, right? We can add over the fraction. And now, on the left-hand side, that's 2 divided by 1, so you could cross multiply and get 2x squared equals 180,000. And then you can divide by 2 and get x squared equals 90,000. And now you have to take the square root of this. Now, some of you might be going, uh-oh, is this a no-calc question? And the answer is yes, right? So if you think about it this way, right, you know, if x squared was just 9, the answer is 3. And then what's the square root of 10,000? 10,000 is 100 times 100. And so 3 times 100, you get 300. Technically, negative 300 is also a solution to that equation, but not in my domain, right? X can't be negative. And so we just cross that out. And of course, don't forget, we have to set p prime equal to does not exist. Now, this is one of the rare cases there is a solution to this, right? Because p prime, right, has a variable in the denominator. What if x was 0? That fraction would be undefined, right? So you could say that's a critical number, but again, we have a domain issue, right? And so my only critical number is actually positive 300. Okay, so the last step is confirming that this is either a max or a min. Okay, now for example 1, right, I'm going to go back real quick, right? We did first derivative test, and for first derivative test, you have to know the domain, right? Because you have to know what range you have to pick your numbers, okay? And so here's the thing though, right? What else did we say with example 1? You don't have to do first derivative test, right? We also learned second derivative test in unit 5, and so that's just as viable of an option. So here's the nice thing about picking the second derivative test. You don't have to know what the domain is, right? Now, remember though, the second derivative test can fail, right? And that's when, you know, you plug in your critical number into the second derivative and you get 0, right? Then you have to go first derivative test and you have to know the domain. So I've had a lot of students in the past who will struggle with finding the domain, right? If you're going to go second derivative test, right, you don't have to know what the domain is, right? Because you just have to find your second derivative, right? And so let's look back at p prime. Right, so the derivative of 2 is 0, so we ignore that. Negative 180,000 x to the negative second, right? So that's just power rule, and so that would become, right, bring the negative 2 down, so it would be positive 360,000 x to the negative third. But again, I don't like negative exponents, okay? And now I have to plug my critical number into that second derivative I just found. Remember, all you care about is the concavity at the critical number. All you care about is it positive or negative? If I do 360,000 divided by 300 cubed, I don't care how big or small that number is, right? What I do care about is that it's a positive over a positive, and so we get a positive, meaning we are concave up at this critical number, meaning x equals 300 is my minimum. Okay, no endpoints to check, right? And so this is my only answer. And now we go back, excuse me, and we answer the question, right? What dimensions would require the least amount of fencing? We just found that x equals 300 is our minimum, and so we need to now figure out what y is. And so we have to do 180,000 divided by 300. And remember, you can cancel off the 2 zeros at the end of each of those. So you can just do 1,800 divided by 3, and you get 600. And now the last thing again, make sure you answer the question, right? What dimensions? This question has units, square meters for the area, and so the dimensions must be given with meters. Okay, so that was example 2, and I'll see you next time for example 3.